We're going to talk about something called electrostatics or electrostatic charge. Electrostatics is the study of the nature, behavior, and use of electricity that is stationary and related phenomenon to that electricity. Electrostatics is to be compared to what we will talk about in the next couple of weeks, or electrical current, which is the study of electricity that is in motion or in current. Electrostatics, the electrons or the electrical charges are not moving, which is why you have the word statics in as part of the word electrostatics. And this electrostatics has certain phenomena that you can take advantage of and use in real life. So what is the nature of static electricity? First of all, you have something called an electrical charge. An electrical charge is a property of any particle or item that allows them to attract or repel other particles or bodies that also have charges. And these attractions or repulsions come from the electromagnetic force that is generated from an electrical charge. Now, the diagram you see on your slide shows a positive charge, and it shows the lines of electromagnetic force radiating out with the arrowheads pointing out, and that is the convention. The convention is that the electromagnetic force travels from the positive charge to the negative charge. And so when you see a positive charge with lines of force, the lines of force will be drawn such that the arrowheads are pointing away from the electrical charge. Also, I want to point out that the lines of force radiate out from a 360-degree pattern. That is, they're equal in all directions. And that is important to remember about electrical charges and electromagnetic force. So there are two types of charge. They're opposite. There's the positive charge, which is embodied in the proton, which is in the center of the nucleus, and the electron, which travels outside the nucleus and it embodies the negative charge. Electricity is a term that's used for the interaction between electrons and other charged particles and other non-charged particles. Now notice this diagram shows an electron which has a negative charge. And notice the lines of force, again, radiate around the electron in 360 degrees, but now the arrowheads point toward the electron. And again, this is the convention to show. In the previous slide, we had a positive with the lines of force radiating out from the positive force, and now we have a negative with the lines of force radiating toward the electron. Neutral is an atom which has an equal number of positive and negative charges. Thus, an equal number of electrons and protons, and this equal and opposite charges neutralize each other as they touch each other. And so a normal atom, a normal body that's in space, is neutral if all the electrical forces counteract each other, and there are no electromagnetic or lines of force that radiate out from such a body. Static electricity, or electrostatics, is a phenomenon that occurs while the electrons or the charges are not moving. In the future, we'll be talking about electricity as well as magnetism, both of which occur as a result of the motion of electrical charges as opposed to static electrical charges. An electrical field is a region around a static charge where the attraction or repulsion can occur. And here the electrical field's being shown. And you'll notice again that the arrowheads in general are heading away on one side and toward on another side. Now there's a reason for that, which I can't really show on this slide, but it's common, depending on the direction of the electrical charge's motion, or if it's not moving, whether it's a positive or negative, there's a way in which this is delineated. This is actually a picture that would be related to the motion of electrical charges, not static charges. You can see the little arrowhead in the middle indicates the direction that the electrons are moving. And with the electrons are moving in that direction, then the electrical field will be in this pattern. If it were moving the opposite direction, it would be exactly the opposite. But the field itself, delineated by these lines, is the region around which the repulsion or attraction occurs. And the mapping of that field are called lines of force. Now, these lines don't actually exist. They're imaginary lines that are used to draw the resulting field, but they're not actual lines that you could see if you had a microscope that was powerful enough. The coulomb, and we will be talking about coulombs in the next few weeks, is the SI unit for electrical charge equivalent. And it is equivalent to 1 coulomb is equal to the charge that can be generated by 6.240 times 10 to the 18 electrons. You may or may not remember that a mole of material is the amount of material that contains 6.02 times 10 to the 23rd molecules or atoms. Well, a coulomb of charge is the charge that resides in the aggregate of 6.24 times 10 to the 18 electrons, which means that one electron has the charge of 1.0609 times 10 to the minus 19 coulombs. Now, the law of charges is actually very simple. The law of charges states that opposite charges attract and similar charges repel. Opposite charges attract and similar charges repel. So, at the top here on this diagram on the left, you have a positive and a negative, and those two will be attracted to each other. Whereas two positives or two negatives will repel each other. And it is actually possible to calculate the force of attraction or repulsion of those charges. The field around which this occurs is called a uniform field, and it's the area where the electrical force is equal throughout. So there is an area between the positive and negative, or between the two positives or the two negatives, where there's equivalent electrical force, either of attraction or repulsion, that occurs throughout. Now, the law of charges can be described mathematically by the law of electrical force, and that's given here. The law of electrical force states that the force is equal to a constant, which is approximately 8.99 times 10 to the 9th newtons, times the charge of the first body times the charge of the second body divided by the distance between the two bodies squared. Now, you might notice that this has a very similar format to the universal gravitational law. The gravitational law, if you remember, was a constant times the mass of the first object times the mass of the second object divided by the distance between the two. And so these two, and there are other formulas like this, these two formulas are very similar. And so you can do calculations of the force between two bodies, and if the bodies are oppositely charged, it'll be a force of attraction, and if the bodies are similarly charged, it'll be a force of repulsion, and it's calculated using this formula. So let's do a couple of problems. Well, here is an example, and you can see I told you that the constant is 8.99 or 9 times 10 to the 9th newtons per meter squared, Newton meter squared per coulomb squared. And the distance is the distance between the centers of the two charged particles. So let's do a couple problems, and there will be a problem like this on the quiz associated with this chapter. And we'll do a couple of them to give you an idea of how to do it. They're not really very hard. So let's look at the first one. Suppose that there are two balls, insulated balls, that are separated by 1 meter, and each has a charge that is 1 coulomb. Now, it says 1, so you'll have to assume that that's positive 1 coulomb. What is the magnitude of the electrostatic force felt by one of the spheres due to the electrical force from the other sphere? So let's take a look at how we would do that. Remember, the formula was that the force is equal to the constant, which we gave right here, times the first charge times the second charge divided by the distance between them. Or I think I said d squared in the formula. Well, each of these charges, so we have 8.99 times 10 to the 9th, and that's Newton meters squared per coulomb squared. And it's important to keep that straight because sometimes this distance is not in meters and sometimes you have to correct it. In this case it is. And so that's going to be multiplied by the 1 coulomb charge of the first and times the 1 coulomb charge of the second. And all of this will be divided by 1 meter distance between them squared. Now the math here is real simple, and you end up with 8.99 times 10 to the 9th newtons. And that, it's actually, because there's two significant figures, it's more appropriately to say 9.0 times 10 to the 9th newtons is the force. Now, because they're both positive, this will be a force of repelling or repulsion. And so if you were to draw these like this, you would have to say that the direction, and each of these would experience the same. This would experience 9 times 10 to the 9th newtons from right to left, and this one at the same time would experience 9 times 10 to the 9th newtons from left to right. And so that's the first problem. Now the second problem is just a little more challenging. It says, what's the magnitude of the force between a proton and an electron in a hydrogen atom if the distance is 0.53 times 10 to the minus 10? Again, it's the same formula. You have K times Q1, Q2 divided by R squared. Now, if you have trouble remembering it, remember that a coulomb is 6.24 times 10 to the 18 electrons. It's the charge of 6.24 times 10 to the 18 electrons. Now that means that any one electron has a charge of 1.603 times 10 to the minus 19 coulombs. That's 1 over this number right here. And so that's the charge of an electron. It'd be negative if it's the charge, and the charge of a proton is exactly the same, but it's going to be a positive 1.603 times 10 to the minus 19. And so we put that in here. We have F is equal to 8.99 times 10 to the 9th times 1.603 times 10 to the minus 19, and I'm just going to say squared, although one of them is positive and one of them is negative. We can remember that. And that's going to be divided by this distance, 0. This is actually not correct. It should be 5.3 times 10 to the minus 9 meters, and that distance is going to be squared. So that's going to be, if we do the math here, first we square that number and multiply it by 8.99 times 10 to the 9th, and we take all of that and divide that. We divide that by 5.3 times 10 to the, here we get 8.22 times 10 to the minus 36912 newtons. So the force between a proton and an electron in a hydrogen atom is 3.22 times 10 to the minus 12. And since one is positive and one is negative, this force will be an attractive force, which means it will attract. It's a force of attraction, which means it will attract the electron toward the center of the nucleus.